Picture this. A massive wooden frame towers 20 feet above the battlefield. Twisted sinew cables, thick as a man's arms, strain under impossible tension. Roman engineers step back as their captain raises his hand. The target, an enemy fortress wall, 300 yards away, stands defiantly against the might of Rome. In less than a heartbeat, a stone projectile weighing 60 pounds tears through the air at over 100 miles per hour, shattering ancient masonry like pottery. This is the Ballista, Rome's deadliest artillery machine. And today we're about to discover just how this engineering marvel changed the face of warfare forever. Welcome back to our channel, fellow history enthusiasts. I'm your host, and today we're stepping into the sandals of Roman engineers and soldiers to witness one of antiquity's most devastating weapons in action. If you're passionate about uncovering the ingenious technologies that shaped our world, make sure to hit that subscribe button and join our growing community of over subscriber count history lovers who never miss an epic story from the past. The year is the Mediterranean world trembles under the advancing legions of Rome. But it's not just the disciplined infantry or skilled cavalry that strikes fear into enemy hearts. It's the thunderous roar of Roman artillery that announces the empire's arrival. Among these mechanical marvels, none was more feared, more effective, or more ingeniously designed than the ballista. But what made this ancient war machine so devastatingly powerful? How did Roman engineers harness the fundamental forces of physics to create a weapon that could punch through stone walls, shatter enemy morale, and help build the greatest empire the world had ever known? Today we're diving deep into the mechanics, the history, and the battlefield impact of Rome's deadliest artillery piece. The stakes couldn't have been higher. In an age where siege warfare could determine the fate of entire civilizations, the ballista represented the cutting edge of military technology, a perfect fusion of Greek mathematical genius and Roman engineering pragmatism that would dominate battlefields for over 6 centuries. Our story begins not in the workshops of Rome, but in the brilliant minds of ancient Greek engineers. Around 400 BCE, as city-states waged constant warfare across the Hellenic world, military engineers began experimenting with ways to amplify human strength using mechanical advantage. The first primitive catapults were little more than giant crossbows, but they planted the seed of an idea that would revolutionize warfare. Enter Ctesibius of Alexandria, the Leonardo da Vinci of the ancient world, working in the Great Library of Alexandria around 270 BCE. This mechanical genius didn't just improve existing designs, he revolutionized them entirely. Ctesibius understood something that would make the ballista legendary: the incredible power stored in twisted sinew and rope under tension. Picture the workshop of this ancient inventor. Papyrus scrolls covered in geometric diagrams scatter across wooden tables. Bronze gears and pulleys gleam in the Mediterranean sunlight streaming through high windows. The air buzzes with the excitement of innovation as Ctesibius and his apprentices test different materials, different angles, different tensions. They're not just building weapons, they're unlocking the secrets of stored mechanical energy. The breakthrough came when Ctesibius realized that by twisting bundles of sinew or rope into torsion springs, he could store enormous amounts of energy in a compact mechanism. This wasn't just an improvement, it was a quantum leap in military technology. The torsion-powered ballista was born, and with it the future of siege warfare. But it was the Romans, with their legendary practical engineering skills, who would perfect this devastating machine. Around 50 BCE, as Rome's legions marched across 3 continents, military engineers like Marcus Vitruvius began standardizing and improving Greek designs. The Romans didn't just want weapons, they wanted weapons that could be mass-produced, easily maintained and operated by soldiers, rather than specialist engineers. Now let's strip away the mystique and examine the brilliant engineering that made the ballista so devastatingly effective. Imagine standing before a fully assembled Roman ballista, a monument to ancient engineering that towers above you like a wooden titan of war. The heart of this machine lies in 2 vertical frames, each containing a twisted bundle of sinew, rope, or animal hair under tremendous tension. These torsion springs, called skeins by the Romans, were the powerhouse of the entire system. Picture the painstaking process of creating these springs. Roman engineers would take strips of fresh sinew from slaughtered animals, twist them into tight bundles, then thread them through bronze rings with mechanical precision. The tensioning process was an art form in itself. Using a windlass, a horizontal rotating cylinder operated by handles, engineers would slowly twist these skeins until they reached optimal tension. Too little, and the ballista lacked power. Too much, and the sinew would snap, potentially killing anyone nearby. Roman military manuals specified exact measurements and tensions based on the size of projectile and desired range. Through the center of each torsion spring passed a wooden arm, connected at the center by a bowstring made of twisted. When pulled back using a winch system, these arms stored the rotational energy of the twisted springs. The mechanical advantage was enormous. Where a human might generate 100 pounds of draw weight with a bow, the ballista could store over 2,000 pounds of. But here's where Roman engineering genius truly shone: the trigger mechanism. Unlike crude early catapults that required multiple men to release, the ballista featured a sophisticated trigger system operated by a single soldier. A bronze trigger connected to a release mechanism allowed for precise timing and accuracy that made this weapon not just powerful but deadly precise. The projectile itself sat in a carefully carved wooden channel perfectly aligned with the weapon's trajectory. Roman engineers understood ballistics in ways that wouldn't be formally studied until centuries later. They calculated optimal angles, accounted for projectile weight, and even developed different types of ammunition for different tactical situations. Behind every great weapon stands a great mind, and the ballista was no exception. Let's meet the forgotten heroes, whose genius made Rome's artillery supremacy possible. The military engineers who combined theoretical knowledge with battlefield pragmatism to create mechanical marvels. Marcus Vitruvius Pollio stands as perhaps the greatest military engineer of his age. Writing during the reign of Augustus Caesar, around 25 BCE, Vitruvius didn't just build ballistae, he wrote the definitive manual on their construction and operation. His work, De Architectura, contains detailed specifications that modern engineers have used to build working replicas. Picture Vitruvius in his workshop, surrounded by the tools of his trade. Wooden models demonstrate mechanical principles while bronze measuring instruments ensure precision. But this isn't just theoretical work. Vitruvius has seen combat. He's watched his machines smash enemy fortifications and witnessed firsthand what happens when engineering meets warfare. According to Vitruvius, the perfect ballista operator needed to be part mathematician, part mechanic, and part warrior. These specialists, known as ballistari, underwent extensive training not just in operating their weapons, but in maintaining, repairing, and even building them in the field. They were among the highest paid soldiers in the Roman army, and for good reason. Their skills could determine the outcome of entire campaigns. The engineering principles these men mastered were sophisticated beyond their time. They understood concepts like elastic potential energy, mechanical advantage, and projectile physics, centuries before these became formal scientific discipline. Roman military engineers calculated the relationship between torsion spring diameter and projectile weight with mathematical precision that rivals modern artillery calculations. But perhaps most impressively, they designed their weapons for battlefield practicality. Every component could be disassembled and transported by mule train. Replacement parts were standardized across the empire. Operating procedures were documented and taught systematically. This wasn't just brilliant engineering, it was brilliant military logistics. The creation of a Roman ballista was a masterpiece of ancient manufacturing that rivaled the complexity of building a modern automobile. Let's step into the workshops of the Roman military, where master craftsmen transformed raw materials into engines of war, through a process that took months of meticulous labor. The journey began in the forests of the empire, where military procurement officers selected specific types of wood for different components. Oak provided strength for the frame and arms, while elm offered flexibility for moving parts. Pine was chosen for projectile channels due to its straight grain and light weight. Roman military manuals specified not just the type of wood, but the season when it should be harvested and how long it must be seasoned before use. In the bronze foundries, master metallurgists crafted the dozens of bronze fittings that held each ballista together. The torsion rings, which contained the twisted sinew springs, required precise manufacturing tolerances. Too loose, and the springs would lose tension. Too tight, and they would bind under load. Roman engineers developed specialized tools and techniques to ensure each bronze component met exact specifications. The most challenging component was the torsion springs themselves. Master sinew workers, drawn from the ranks of experienced bowyers and string makers, would select prime animal sinew from freshly slaughtered cattle. The sinew was carefully prepared, cleaned and treated with oils to maintain flex. Each spring contained hundreds of individual sinew strands, twisted together with mathematical precision to achieve optimal power storage. Assembly required a team of specialists working in perfect coordination. The frame was erected first, carefully squared and braced. The bronze fittings were installed with millimeter precision. Then came the delicate process of installing and tensioning the torsion springs, a procedure that could take days and required constant adjustment to achieve perfect balance. Quality control was rigorous. Each completed ballista underwent extensive testing, firing hundreds of practice rounds to ensure reliability. Roman military standards demanded that every weapon be capable of firing continuously for hours without failure. The empire's reputation and the lives of its soldiers depended on this mechanical precision. Now comes the moment we've been building toward, witnessing the ballista in action on the battlefields that shaped history. Close your eyes and imagine the thunderous symphony of ancient warfare, where the crack of releasing ballistae provided the deadly percussion that announced Rome's military might. Our first stop is the siege of Masada in 73 CE, where Roman engineering faced its ultimate test against Jewish rebels, who had turned the mountain fortress into a seemingly impregnable stronghold. The Roman commander Flavius Silva faced a challenge that had broken other armies. How do you assault a fortress perched on a cliff 400 feet above the desert floor? The answer lay in Roman artillery supremacy. Silva's engineers positioned dozens of ballistae around the base of Masada, their bronze-fitted frames gleaming in the harsh desert sun. But these weren't ordinary siege weapons. They were precision instruments of psychological as well as physical warfare. Picture the morning of the assault. Roman soldiers, their movements coordinated like a deadly dance, load the ballistae with specially crafted stone projectiles, each weighing between 30 and 60 pounds. The weapons are aligned using sophisticated sighting mechanisms that allowed for precision targeting at ranges exceeding 400. As Silva raises his crimson banner, dozens of weapons crews begin their synchronized loading sequence.
The command rings out across the desert morning. In perfect unison, triggers are released, and the air fills with the thunderous crack of twisted sinew, unleashing its stored energy. The projectiles, visible as dark streaks against the brilliant blue sky, arc upward toward the fortress walls with devastating precision. The psychological impact was as important as the physical damage. Defending soldiers who had felt secure behind their stone walls suddenly found themselves under bombardment from weapons that could strike any point within their fortress. The constant thunder of artillery, continuing day and night for weeks, wore down defender morale in ways that direct assault never could. But the ballista's battlefield effectiveness wasn't limited to siege warfare. During the conquest of Gaul, Julius Caesar's legions used portable ballistae as field artillery, providing covering fire for advancing infantry and breaking up enemy formations before they could close to combat range. At the Battle of Gergovia in 52 BCE, Caesar's artillery played a crucial role in one of his most challenging campaigns. Facing Vercingetorix's warriors positioned on high ground, Caesar deployed his ballistae to neutralize Gallic advantages in terrain and numbers. Roman military accounts describe the devastating effect of concentrated artillery fire on massed barbarian formations, projectiles that could kill multiple warriors with a single shot, creating gaps in enemy lines that Roman infantry could exploit. The technical capabilities of these weapons were truly remarkable. Modern reconstructions have demonstrated that Roman ballistae could achieve muzzle velocities exceeding 100 miles per hour, delivering projectiles with kinetic energy equivalent to a modern artillery shell. The largest models, known as onagers, could hurl stones weighing over 100 pounds to ranges exceeding 500 yards with accuracy that allowed trained crews to target specific sections of enemy fortifications. Roman military engineers never stopped innovating, and the ballista evolved through dozens of specialized variations designed for specific tactical situations. Like a Swiss Army knife of ancient warfare, different models served different battlefield roles with mechanical precision that showcased the empire's technological supremacy. The standard field ballista, known as the Scorpio, was designed for mobility and rapid deployment. Weighing approximately 85 pounds when disassembled, it could be carried by a single mule and assembled by 2 men in under 30 minutes. These weapons formed the backbone of Roman artillery, providing direct fire support for infantry operations and defensive fire for fortified positions. But for siege warfare, Roman engineers developed true monsters of mechanical engineering. The largest ballistae, sometimes called Ballista, stood over 20 feet tall and required crews of 8 to 10 men for operation. These weapons could hurl projectiles weighing over 100 pounds with such force that they could punch completely through stone walls 3 feet thick. Perhaps most ingeniously, Roman engineers developed specialized ammunition for different tactical situations. Standard stone balls provided maximum kinetic energy for smashing fortifications. Iron-tipped bolts, some over 6 feet long, were designed to penetrate multiple ranks of enemy soldiers or punch through shield walls. Incendiary projectiles, wrapped in oil-soaked cloth, could set fire to enemy structures or ships. For anti-personnel work, Roman artillery crews used a particularly nasty innovation, the grape shot equivalent of ancient warfare. Leather bags filled with iron caltrops or sharp stones would burst upon impact, creating devastating anti-infantry effects, similar to modern fragmentation shells. The psychological impact of these weapons was enormous, as enemy soldiers never knew whether the next projectile would target fortifications or personnel. The mechanical sophistication of these weapons reached its peak in the later empire with the development of repeating ballistae. These weapons, described in military manuals from the 4th century CE, could fire multiple projectiles in rapid succession using an ingenious magazine feeding system. While these weapons were mechanically complex and required highly trained crews, they provided unprecedented rates of fire that could break up enemy assaults through sheer volume of projectiles. Roman engineers also developed specialized siege versions that could be assembled inside protective wooden towers, allowing artillery crews to engage enemy positions while remaining protected from counter-battery fire. These tower-mounted ballistae played crucial roles in siege warfare, providing covering fire for sappers and assault troops while remaining immune to most defensive measures. History's greatest military campaigns often turned on the thunderous crack of ballista strings and the crash of stone against fortified walls. Let's witness some of the most spectacular demonstrations of Roman artillery power, where engineering genius met battlefield brilliance to forge an empire that would last 1,000 years. The Siege of Jerusalem in 70 CE stands as perhaps the greatest showcase of Roman artillery supremacy in action. The future Emperor Titus, commanding 4 full legions against the most heavily fortified city in the ancient world, faced defenses that had been strengthened and reinforced over centuries. The Jewish defenders, led by charismatic commanders like John of Gischala and Simon Bar Giora, had transformed their city into a fortress that seemed impregnable to conventional assault. But Titus brought with him something unprecedented in siege warfare, a concentrated artillery park of over 200 ballistae of various sizes, supported by specialized siege equipment that represented the pinnacle of Roman military engineering. Picture the scene as Roman engineers worked through the spring nights of 70 CE, assembling their mechanical army within range of Jerusalem's walls. As dawn broke over the ancient city, the Romans unleashed the most concentrated artillery bombardment in ancient history. The air filled with the symphonic thunder of hundreds of weapons firing in coordinated volleys. Stone projectiles weighing up to 100 pounds crashed into Jerusalem's walls with such force that entire sections of ancient masonry simply disintegrated. The psychological impact was overwhelming. Defenders who had never faced such concentrated firepower found themselves under assault from weapons that could strike any target within the city with devastating precision. The Jewish historian Josephus, who witnessed the siege firsthand, described the ballista fire as stones flying like white birds through the air. He wrote of how defenders would post lookouts to watch for incoming projectiles, shouting warnings like "the sun comes" when they spotted the white stones arcing through the sky. But the weapons were so accurate and fired so rapidly that even warned defenders often couldn't escape in time. Roman artillery tactics during the siege demonstrated sophisticated understanding of combined arms warfare. Light ballistae provided covering fire for engineering works and kept defenders away from the walls. Heavy weapons systematically dismantled fortifications piece by piece. Specialized incendiary projectiles set fire to defensive structures and supply warehouses. The coordination required to manage hundreds of artillery pieces while simultaneously conducting infantry operations showcased Roman military professionalism at its peak. The siege of Alesia in 52 BCE offers another spectacular example of ballista effectiveness in field warfare. Julius Caesar, facing Vercingetorix's massive army of Gallic warriors, found himself surrounded and outnumbered in what seemed like an impossible tactical situation. But Caesar's genius lay not just in his strategic double wall construction, but in his use of concentrated artillery fire to break up enemy attacks before they could reach Roman fortifications. Caesar's engineers positioned ballistae at regular intervals along both walls, creating interlocking fields of fire that could devastate any attacking formation. When Vercingetorix launched his massive simultaneous attack on both Roman positions, Caesar's artillery played a crucial role in breaking up coordinated assaults. The weapons were used not just for direct fire against enemy formations, but for precision targeting of Gallic commanders and standard bearers, disrupting enemy coordination at critical moments. The battle demonstrated another crucial aspect of Roman artillery doctrine: mobility and rapid repositioning. As the tactical situation changed, ballista crews could quickly relocate their weapons to threatened sectors, providing concentrated firepower wherever it was needed most. This flexibility, combined with the weapon's accuracy and rate of fire, gave Roman commanders tactical options that their enemies simply couldn't match. Behind every devastating volley of ballista fire stood men whose skills represented years of intensive training and battlefield experience. The ballistae, Rome's artillery specialists, were among the most highly trained and well-paid soldiers in the legions, and for good reason. Their expertise could determine whether a siege lasted weeks or months, whether an assault succeeded or failed in bloody repulse. The training of a ballista crew began with selection of candidates who demonstrated not just physical strength, but mechanical aptitude and mathematical skill. Roman military manuals specified that potential ballistae should be able to perform complex calculations involving projectile weights, spring tensions, and firing angles. They needed steady nerves under pressure, precise hand-eye coordination, and the ability to work as part of a closely coordinated team. Picture a training camp somewhere in the Roman countryside, where experienced veterans put raw recruits through months of intensive instruction. The training began with basic mechanical principles: how torsion springs stored and released energy, how different projectile weights affected trajectory and range, how weather conditions influenced weapon performance. Students learned to identify different types of targets and select appropriate ammunition and firing angles. But theoretical knowledge was just the beginning. Trainees spent hours each day practicing the complex choreography of ballista operation. Loading sequences had to be performed with mechanical precision under combat stress. Aiming procedures required split-second calculations and adjustments. Most challenging of all, crews had to learn to maintain and repair their weapons under battlefield conditions, often while under enemy fire. The most skilled ballistae were those who could perform field modifications and adjustments to optimize their weapons for specific tactical situations. They learned to adjust spring tensions for different ranges, modify projectiles for special effects, and even jury-rig repairs using battlefield materials when proper replacement parts weren't available. Veterans of multiple campaigns developed almost supernatural skill with their weapons. Roman military accounts describe artillery crews who could consistently hit man-sized targets at ranges exceeding 200 yards, or who could place projectiles through specific openings in enemy fortifications with uncanny accuracy. These master gunners were so valuable that they often received special protection details and premium pay rates. The esprit de corps among ballista crews was legendary. These units developed fierce pride in their technical skills and battlefield effectiveness. They competed constantly to achieve the longest accurate shots, the fastest loading times, and the most spectacular target destruction. This competitive spirit drove continuous innovation and improvement in artillery techniques throughout the empire's history. To truly appreciate the ballista's devastating effectiveness, we need to understand the sophisticated physics and engineering principles that Roman military engineers mastered centuries before these concepts became formal scientific discipline. The ballista represented a perfect fusion of theoretical knowledge and practical application that showcases the remarkable technical sophistication of ancient Rome. At its heart, the ballista was an elegant demonstration of energy storage and transfer. The torsion springs, twisted bundles of sinew or rope, functioned as mechanical batteries, storing enormous amounts of elastic potential energy that could be released instantaneously. Roman engineers understood intuitively what we now call Hooke's law, the principle that the force exerted by a spring is proportional to its displacement from equilibrium position. The mathematics involved were surprisingly sophisticated. Roman military manuals contained detailed calculations for determining optimal spring tensions based on projectile weight and desired range. Engineers calculated the relationship between torsion spring diameter and maximum energy storage capacity. They understood that doubling the diameter of a torsion spring increased its energy storage capacity by a factor of 4, a principle that wouldn't be formally stated until much later in scientific history. The mechanical advantage provided by the ballista's lever system was enormous. Where a human archer might generate 100–200 pounds of draw weight, a ballista could store over 2,000 pounds of force in its torsion springs. This mechanical advantage was achieved through a sophisticated system of pulleys, windlasses and lever arms that multiplied human input force by factors of 10 or more. Roman engineers also understood projectile ballistics with remarkable precision. They calculated optimal firing angles for different ranges, accounted for the effects of projectile weight and air resistance, and even developed techniques for adjusting fire based on wind conditions and target movement. Modern reconstructions have confirmed that Roman ballista trajectories matched calculated ballistic curves with impressive accuracy. Perhaps most impressively, Roman artillery designers understood the relationship between kinetic energy and target damage. They calculated that a 60-pound stone projectile traveling at 100 miles per hour delivered approximately 20,000 foot-pounds of energy, equivalent to the impact force of a modern artillery shell. This energy, concentrated into the small impact area of a stone ball, was sufficient to penetrate stone walls 3 feet thick or completely destroy wooden fortifications. The precision manufacturing required to achieve this performance was extraordinary. Torsion springs had to be tensioned to within narrow tolerances. Too little tension resulted in reduced range and accuracy, while too much could cause catastrophic failure that killed the crew. Bronze fittings required precise dimensions to maintain proper alignment and prevent binding under load. Even the wooden components were manufactured to exacting specifications that ensured consistent performance under battlefield conditions. The ballista wasn't just another weapon in Rome's military arsenal. It was a revolutionary technology that fundamentally changed the nature of warfare and provided the empire with decisive tactical advantages that proved crucial in establishing Roman dominance across 3 continents. Understanding how artillery integration transformed Roman military doctrine reveals the true significance of this mechanical marvel. Before the widespread adoption of ballista technology, siege warfare was primarily a matter of endurance. Armies surrounded enemy cities and waited for starvation or disease to force
surrender.
The offensive capabilities available to besieging forces were limited to scaling ladders, crude battering rams, and fire arrows that were easily countered by competent defenders. The ballista changed this equation completely by providing siege commanders with precision strike capabilities that could systematically dismantle enemy fortifications. The psychological impact of concentrated artillery fire cannot be overstated. Enemy soldiers who had never faced ballista bombardment found themselves dealing with weapons that could kill at ranges where they couldn't strike back, that could punch through any personal armor or shield, and that created a constant atmosphere of terror and helplessness. Roman military accounts describe how the mere appearance of ballista batteries was often sufficient to encourage enemy surrender without actual combat. But the ballista's strategic impact extended far beyond individual battles. The ability to conduct rapid, decisive siege warfare allowed Roman armies to maintain offensive momentum during campaigns. Instead of spending months or years reducing fortified positions through blockade and starvation, Roman commanders could breach enemy defenses in days or weeks. then continue their advance before enemies could organize effective resistance. This technological advantage was particularly crucial during Rome's expansion into regions with sophisticated defensive architecture. The fortified cities of the eastern Mediterranean, the hilltop strongholds of Spain, and the tribal settlements of Gaul all posed serious challenges to conventional assault technique. Roman artillery provided the capability to overcome these defensive advantages through superior firepower and precision targeting. The economic implications were equally significant. Rapid siege warfare reduced the enormous costs associated with maintaining large armies in the field for extended periods. It minimized casualties among expensive professional soldiers. Most importantly, it allowed Rome to project military power over vast distances by ensuring that fortified positions couldn't serve as permanent obstacles to Roman expansion. Roman artillery also revolutionized field warfare by providing infantry commanders with powerful supporting weapons that could break up enemy formations, eliminate key targets, and provide covering fire for tactical maneuvers. The integration of ballista batteries with traditional infantry tactics created combined arms capabilities that no contemporary military force could match. As we near the end of our journey through the mechanics and battlefield history of Rome's deadliest artillery machine, it's time to examine the ballista's lasting impact on military technology and its influence on the development of artillery that continues to this day. The principles pioneered by Roman engineers echo through centuries of military innovation, connecting ancient mechanical genius to modern warfare. The ballista's most important contribution to military technology was demonstrating the devastating potential of mechanically amplified projectile weapons. While individual bows and crossbows had existed for centuries, the ballista proved that engineering ingenuity could create weapons with power levels previously unimaginable. This concept, using mechanical advantage to multiply human strength, became the foundation for every artillery development that followed. Medieval siege engines like the trebuchet and mangonels were direct descendants of Roman torsion artillery, adapting ballista principles to different mechanical systems. Renaissance cannon makers studied Roman military treatises and incorporated ballista design principles into early gunpowder weapons. Even modern artillery retains fundamental concepts pioneered by Roman engineers: the importance of precision manufacturing, systematic crew training, and integrated fire control system. The ballista also established artillery as a distinct military specialty requiring dedicated training, specialized equipment, and tactical doctrine. The Roman model of professional artillery crews, standardized equipment, and systematic training programs became the template for military organizations throughout history. Modern artillery units trace their organizational structure and professional traditions directly back to Roman ballista batteries. Perhaps most significantly, the ballista demonstrated the strategic importance of technological superiority in military affairs. Rome's ability to develop, manufacture, and deploy superior weapons technology was crucial to the empire's success and longevity. This lesson that technological advantage can compensate for numerical disadvantage and provide decisive military superiority remains as relevant today as it was 2,000 years ago. The engineering principles embodied in the ballista also influenced civilian technology development. Roman understanding of mechanical advantage, energy storage, and precision manufacturing found applications in construction equipment, agricultural machinery, and industrial mechanisms. The same mathematical principles used to calculate ballista performance were applied to aqueduct construction, bridge engineering, and architectural projects that showcased Roman technical sophistication. Modern reconstructions of Roman ballista, built using ancient techniques and materials, have provided remarkable insights into the sophistication of Roman engineering. These working replicas demonstrate that Roman artillery achieved performance levels that weren't surpassed until the development of gunpowder weapons over a millennium later. Some aspects of Roman ballista design, particularly their accuracy and rate of fire, remain superior to early cannon for centuries. The ballista's influence extends beyond purely military applications into the realm of engineering education and historical understanding. Modern engineers studying Roman artillery development gain insights into mechanical design principles, manufacturing techniques, and system integration approaches that remain relevant to contemporary technology. The Ballista serves as a masterclass in practical engineering that combines theoretical knowledge with battlefield requirements. Archaeological discoveries continue to reveal new aspects of Ballista technology and deployment. Recent excavations at Roman military sites have uncovered Ballista components, projectiles, and even complete weapons that provide detailed information about manufacturing techniques, tactical employment, and technological evolution. These discoveries confirm that Roman artillery was even more sophisticated and widely deployed than historical accounts suggested. As we stand here at the end of our exploration into Rome's deadliest artillery machine, it's impossible not to feel a sense of awe at the engineering genius and battlefield effectiveness of the Ballista. This wasn't just a weapon, it was a technological revolution that changed the face of warfare and helped establish the greatest empire in human history. From the brilliant Greek engineers who first harnessed the power of torsion springs, to the Roman military specialists who perfected these machines for battlefield deployment, the Ballista represents humanity's remarkable ability to combine theoretical knowledge with practical innovation. The physics principles mastered by ancient engineers, the manufacturing precision achieved by Roman craftsmen, and the tactical sophistication demonstrated by Ballista crews showcase technical capabilities that remained unmatched for over 1,000 years. But perhaps the most striking aspect of the Ballista's story is how it demonstrates the eternal human drive to push the boundaries of what's possible. These ancient engineers didn't just accept the limitations of existing weapons, they reimagined what warfare could be. They turned mathematical principles into mechanical reality. They transformed raw materials into instruments of empire-building precision. The thunderous crack of Ballista strings may have fallen silent on ancient battlefields, but the legacy of Roman artillery innovation continues to influence military technology, engineering, education, and our understanding of what human ingenuity can achieve when theoretical knowledge meets practical necessity. In our modern age of guided missiles and smart weapons, it's humbling to remember that 2,000 years ago, Roman engineers achieved levels of accuracy, reliability, and battlefield effectiveness that established them as masters of military tech. The Ballista reminds us that true innovation isn't just about having advanced materials or sophisticated tools. It's about combining deep understanding of fundamental principles with relentless dedication to practical excellence. What did you think of Rome's incredible artillery technology? Were you as amazed as I was by the sophisticated engineering and devastating battlefield effectiveness of the Ballista? Let me know in the comments below. I love hearing your thoughts and questions about the incredible innovations that shaped our world. If you enjoyed this deep dive into ancient military technology, make sure to smash that like button and subscribe to our channel for more epic stories from history. We've got amazing content coming up on medieval siege warfare, the engineering marvels of the Renaissance, and the technological innovations that changed the course of human civilization. Ring that notification bell so you never miss an upload, and consider sharing this video with fellow history enthusiasts who appreciate the incredible ingenuity of our ancestors. Together, we're building a community of people who understand that the past isn't just ancient history, it's the foundation of everything we've achieved. Until next time, keep exploring the incredible stories that made our world, and remember, the greatest innovations often come from combining ancient wisdom with relentless curiosity about how things really work.